class. Welcome to the next section in our series, chapter 13.5. Today we're going to discuss the convergence of alternating series. So remember, alternating series are series where the terms vary in sign from one to the other. So it goes positive, negative, positive, negative, positive, negative, so forth, so forth. Okay. So the alternating series test. So if we have an alternating series, um, of this form. Here, notice that our first term, since this is n minus 1, so if we plugged in 1 here, we would have 0. That means our first term would be positive. Okay, so we're going to say that our alternating series start with a positive term and then alternate negative, positive, etc., etc. Okay, each of the terms themselves being positive, so obviously if this term here was negative, this would be now negative, positive, negative, positive, and so forth. So we're assuming that we start with a positive term and then we alternate in form. Okay. So let's say that this series satisfies two conditions. First condition being that each new term is less in value or equal in value to the one before it, right? So the absolute value, I guess, would be an easy way of thinking about this, but the actual value of the term B2 without the plus or minus that's attached to it, just the value here, should be less in value than B1. B3 should be less in value than B2. B4 should be less in value than B3, and so forth and so forth. So the values of the terms as I move forward is getting smaller and smaller every time I move forward, okay? Or is equal in value. Okay, the second condition is that the limit of the sequence goes to 0 if I take n going towards infinity, okay? If both of these conditions are satisfied, then my series is convergent. Okay, so for an alternating series, what do I need? I need that each term decreases in value from the one previous, and that the limit for the formula for the sequence of terms themselves goes to 0. Okay, so let's look at the alternating series estimation theorem. Okay, and so this is basically saying that if my series is convergent and it converges to a sum, S, okay, where the terms B sub n are always positive, okay, then the sum of my alternating series satisfies and uh, my alternating series satisfies the conditions given above, basically that each term is smaller in value than the one before it, and that the limit of the sequence of terms goes to 0. So it's basically saying that as long as this converges, okay, which it should to a value s, it can't equal s if it's not convergent. If it was divergent, it would equal infinity. So it's basically just putting this condition here. Remember that the terms are 0. Okay, remember that this is only going to converge if it satisfies this series, these conditions for the alternating series test. So if I have an alternating series that converges to a value s, okay, then r sub n, which we call the remainder, is my series subtracted from its partial sum up to sub n. Okay, and now we're putting absolute values here because this series is alternating. Yeah, we're adding a bunch of stuff, but we're adding positive and negative, so it's very possible that this remainder value can be negative or that this difference can be negative. But we've seen this a little bit, I believe, that actually, I think this is the first time. Our remainder, right, is basically us adding up the rest of our terms and subtracting it from where we stop. Actually, we did see this, okay? Um, my remainder is always going to be less than or equal to the value of the next term in the sequence. Okay, so let's look at this for a second and kind of decompress this a little bit, right? I have an alternating series that converges, okay, by the alternating series test, and it converges to some value s, okay? The difference between the actual value of the series and its nth partial sums is the remainder, okay? And that remainder is always less than or equal to just the single value of the next term in the sequence. Okay, so test the series for convergence or divergence. So here we have a series that is alternating. You are not given the form, so first off, we have to figure out what's happening here. Here you can see that this is increasing by 1 each time, 5, 6, 7, 8, 9 on the denominator. the numerator is doubling, right? 2, 4, 6, 8, 10. So first term, second, third, fourth, fifth. So it's very clear that the numerator is 2n. Here we're starting with a negative sign. I know I did say let's assume that this starts positive, but alternating series, it doesn't really matter how it does it, how it alternates. Um, and so this bottom value, we can say it looks like it's probably n plus 4, right? So 2n on top and then n plus 4 on the bottom. That's how we get 5 and then increase by 1. And this is doubling. And then we have this negative sign here, right? We're going to say that this is divergent. Obviously, we would want to look at the general form of the series first, which we kind of did. So we can also just look at it term by term and then notice that we're not going to 0, right? I'm not satisfying this first condition, which is that each new term is smaller than or equal to the one before it. So here I have -2/5, which as a decimal is -0.4, right? Or just zero point 0.4 is really what I'm interested in. This next value is 4/6, which is 2/3. All right, so this is zero point 0.4, and this is 0.666667. So this is already violating that condition that the next value is lower in value than the previous. That's not true here. Every time I move up a value, the value is going up, right? Point 0.4, 0.666667. I don't know what this is as a decimal, but it's almost 1. This one is 1. This one is larger than 1. The next one is also larger than 1. So the absolute value of each term is increasing, right? So that's why I can say that this diverges because it doesn't pass the first part of the alternating series test, right? So the sequence of terms are alternating away from 0, right? The next value in the sequence is not less than or equal to the previous. So I was just going to write this in the opposite direction, but I think writing a strike through it makes it clear that it's failing something in this test, right? It fails the alternating series test. So let's look at the next term. So this one, we do have the general form. This one, we can write out term by term what it looks like, and then we can compare. Or what I can really just, if I, an easier way to do this, when I'm given a general term, is compare my sequence general form with my general form, but putting +1 everywhere, okay? Because that's the next term versus the previous. So in order to check this first condition, I will plug in n plus 1 to my general term. I don't need to worry about this -1 to the n thing because I already know it's alternating because I'm applying the alternating series test. So I just need to look at the value of the terms, right? So if I plug in +1 for n, right, n plus 1 everywhere, and compare it to what I have here, then I can talk about whether or not I'm failing or satisfying the first condition. So if I have e to the negative n plus 1 versus e to the negative n, this is a larger value on top. So when I write this as 1 over e to the negative, or I'm sorry, 1 over e to the n plus 1, I have a larger value in the denominator, which means overall it's a smaller in value. Okay, so when I have n plus 1, each new term is smaller in value than the previous. Okay, if I look at what does this do as n goes to infinity, right? It gets really, really small. This turns over 1 over e to infinity, which means it gets to 1 over some very, very, very large value in the denominator, which means it's very, very small, which means the whole thing goes to 0. Okay. Again, you might want to do a little bit of scratch work here on the side for that because I did not do it for you, right? But it's very easy. It's a very easy limit to calculate. Okay. Since it satisfies both conditions, this alternating series is convergent, right? So let's do the next one. So go ahead and pause the video and try this on your own, and then we'll come back and we will do it together. Okay. So you took some time to try this on your own. So let's go ahead and do this. So again, remember, we're only going to worry about this tan inverse n value when we're checking these conditions, right? We're looking at the general term here. For what's happening, right? So term by term, what happens? Am I decreasing in value? as I move down my series. And then I want to look at the limit in general, right? So if I plug in n plus 1 versus n, it's not necessarily true that the next value is always smaller in value than the previous. So I don't even have to go any further since it fails the first condition. But let's say that we do anyways, just for practice here. If I'm looking at the sequence as we move further and further, I get a constant value, um, right? Not zero. So it doesn't satisfy either of the conditions. So it double fails the test. Okay. Not that that matters. You only need to fail one condition, right? If you can see one that it doesn't satisfy, then you can determine the convergence or divergence just from that. Okay. But here for posterity, we did both just so you can kind of get a little bit more practice. Okay. For the next sequence, we have the alternating series, n to the n over n factorial. Okay, so again, we want to check is each new term less in value than the previous. So we will compare n plus 1 for the general form of the sequence versus what we have here. So if we look at what this looks like, right? This is n times n times, and n factorial looks like this. Looks like we can cancel off one n if we needed to. But if we look at the limit itself, it's very clear that this goes to infinity, right? Comparing what's happening in the numerator, all the values I'm multiplying in the numerator are larger in value than what I have in the denominator, except for the first terms, right? N is larger than n minus 1, n is larger than n minus 2. So the numerator is always larger. And so as I continue to look at what happens, the numerator grows. So I don't even have to look to see what's happening term by term. I can already see here that the limit does not go to 0. So this fails by the second term. Okay, so I don't even have to check the first if the first looks like it's going to be a little bit too difficult. Okay, so again, this is the test for divergence. It also just doesn't pass the alternating series test. And so let's do another example. So let's show that the alternating series of 1 over n to the 6th, alternating in sign, is convergent. Again, this is fairly apparent because it's a p-series, although it is alternating in value. It's very easy just by inspection to tell that each new value is less in value than the one previous, and that the limit of the sequence goes to 0. But we can go ahead and do that anyways. Okay, so we also, besides showing that it's convergent, which is we can do by inspection, we want to know how many terms of the series do we need to add together in order for this to find the sum to within a tolerance of 0.00005, right? So this is tenths, hundredths, thousandths, hundred thousandths, basically. Okay. Okay. So it's very easy for us to tell that each new value is less in value than the previous. Uh, and I know that this goes to 0, okay, since it's an alternating period series. And so this is convergent, okay? Now, if we're looking at the remainder, remember the remainder is the sum minus the nth partial. And from the remainder series, if we just go backwards before we go forward, it is saying that once I get to a certain point, the remainder is always less in value than the value of one of the terms. So I just really need to find one of the terms whose value is less than the tolerance that I set arbitrarily, this 0.000005. And then once I came to that point, since I'm adding up a bunch of stuff that's less than this in value, it never adds enough to make it more than this value, okay? Especially since it is a convergent series, right? So if I look at, in this case, B5, I get 1 over 5 to the 6th, which is 0.00064. And remember, my tolerance was a 5. What do I need? 1, 2, 3, 4. I need the fifth value to be 5 after the decimal. Here I have 1, 2, 3, 4.6 or 64 at the fifth term, okay, which is larger than my tolerance, so that's not the value. So if I look at the next value after that, since this is very, very close, okay, I have 0.00002, which is lower than my tolerance. Okay, so that means I just have to add up the first fifth. Okay, so the remainder needs to be less than the value of the previous of the next term, right? So since my next term is less than 0.0005, and every term after this is less than 0.00002, when I add them all together, it will never add up to this tolerance level that I said. Okay, and so since B6 is a value less than my desired error, I have to add up the first 5 terms to be within this error of um, this tolerance level that I set, okay, which isn't that bad. So adding the 6th term doesn't add enough to the sum in respect to our tolerance level that we wanted. Okay, that's the end of our video. I will see you guys on our next video, 13.6. Thank you.